There we go. Hi everyone, this is Dan Barry. Welcome to the June MAPP webinar. The topic of today's webinar is tropical climate extremes, and we have 5 speakers today. We're going to hear from Gabe Vecchi from NOAA GFDL, Schemm from NOAA CPC, George Hallowell from NOAA AOML, Chuntai Wang, also of AOML, and then Yolande Serra, who's at the University of Arizona. So, Gabe, are you on the line?
Yeah, I'm sorry, on mute. Okay.
No, it's okay, it's okay. So I'm going to switch control over to your computer, and then just share your desktop.
Got it.
Great.
All right. So I'm just going to start now. What I'd like to do today is take you through some work that has gone on in the recent years at GFDL, looking at hurricane prediction across a variety of timescales, and then present to you some newer efforts that I think will be paying off some interesting dividends in the near future and years to come. So just to give you a brief view of the tour we're going to go on, we're going to focus on a lot of the efforts that go on at GFDL, where we've been exploring hurricane prediction not just on centennial timescales and decadal timescales, where many people are aware of our work, but also on timescales from days and months and seasons. So just to orient you of how we are thinking about the prediction problem here at GFDL, is that we want to identify what the sources of and limitations on predictability will be, and as many of you will be familiar, on short time scales, so let's call it roughly hours to a month, although for different phenomena the time scale is different. The main sources of predictability are climatology and the evolution of the climate system or the weather system from initial conditions, sort of like a weather forecast or an El Nino forecast. Then if you want to think on long time scales, the sources and limitations on predictability come from primarily the climate response to some external forcing, changes in land use, radiative forcings of different types, and then there's these intermediate timescales that us and a variety of other places have been exploring, this place where both initial conditions and boundary values matter. And for all of these types of predictions, you need both good observations, models, initialization schemes, and forcing estimates. So on short time scales, many of you will be familiar with the GFDL hurricane forecast model. If you tune in hurricane season, you'll see it on the Weather Channel. And the GFDL hurricane model has a long history, but it continues to be developed and improved. And as an example of the dividends of that improvement are the successful track forecasts for Hurricane Sandy, where GFDL was one of the first operational U.S. forecast models to correctly predict Sandy's left turn. And there's other improvements ongoing with GFDL model, including the use of ensembles and other efforts that should improve the predictions of intensity. Now, on timescales of months, there have been some very interesting results arising with our global atmospheric high-resolution model, HIRAM, we call it, where we've not only been able to recover nice climatology of tropical cyclones, and with perfect SST simulations, the interannual and trend of variability and trend of Atlantic hurricanes, but with a very simple sea surface temperature prediction model, which is persisting sea surface temperature anomalies from the onset of the hurricane season, there's extremely good retrospective skill on hurricane forecast. This figure here shows that this retrospective correlation from 1990 through 2010 is approaching 0.9, and if you look at the most recent 10 years, it exceeds 0.9. This is from a paper by Chen and Lin that recently appeared. And that's a very exciting result, and it really points to something very predictable in hurricane activity. We've been working on longer range forecasts. We've developed a hybrid statistical dynamical forecast system. We call it HIHUF, and we've We've published what seem to be very encouraging results with retrospective, significant retrospective skill from as early as October of the year before. We've been continuing to update our assessment of the skill of this forecast system because retrospective skill isn't the same as forecast skill. And we have a website up there where we invite people to take a look at what we have, play with our data, and see if you can come up with some better ways to assess what we've done. Our experimental prediction for 2013, which has been available since January of this year, is for an active year, and I think that is par for the course with pretty much every other forecast center. Now, we've been also moving into the realm of multi-year forecasts. This is where we start going from where initial value is the dominant source of information to where both boundary value, initial value, boundary value being rate of forcing changes primarily, might play an important role in predictive skill. And we've been assessing with a hybrid forecast system the ability of initialization and rate of forcing to allow us to say something about multi-year changes in hurricane activity. And what you can see in these two panels, the left one shows the ability of two climate models and their average, shown by the color lines, to recover the observed 5-year hurricane count in the Atlantic, so the sum of the 5-year hurricanes, which is the observed is shown in black. And what you see is that only knowing rate of forcing, the models capture something like an increase over the last, say, 40 years, but they do not capture the dominant feature of that time series, which is a sharp uptick in the 1990s. When you initialize these models, and you apply the same hybrid forecasting scheme, you find that the both models are much better able to recover that uptick and provide very nice correlations. So these are, in some sense, perhaps encouraging results. However, I think it's very important with the whole field of decadal prediction and multi-year prediction that we recognize that there's very few degrees of freedom, and so our confidence should be limited by that. And also that the skill arises more from recognizing the 94.5 shift and actually predicting it. Also, there are some issues with observing system changes. If you follow the red line at the very end in the right panel, it shows this dramatic uptick that has not been seen in observations. And we know by doing additional experiments that this sharp uptick is actually an artifact of changing observing systems. And so when we have observing systems changing, it does present a challenge for our predictions and interpreting them. We've also done a lot of work on looking on timescales of decades. GFDL has done a lot of work at trying to understand the ability of us to detect and attribute past changes in hurricane activity. And I think one of the results that we've recently come across and is perhaps reflected in other works in the literature is that in the past century or so, there might have been an offsetting effect between the impact of increasing aerosols at the end of the 21st century and increasing greenhouse gases over the 20th century on expected response of hurricane intensity, so that the decrease that aerosol increases would have expected to offset the greenhouse-induced intensification of hurricanes, and so we may not expect to have seen a hurricane increase in the record. However, our model projections are indicating that going forward, the aerosols and the greenhouse gases will be pulling in the same direction. Aerosol reductions will help intensify hurricane activity, and so that the radiatively forced signal over the coming decades may not be the same as that which we've seen over the past century or so. Now, looking even further still, looking at the end of the 21st century, we've been using a hybrid multiple dynamical downscaling technique to get at the changes in frequency of the most intense storms and trying to probe different sources of uncertainty. And the overall result that we've been coming across is that models are suggesting perhaps a decrease at the end of the 21st century in the frequency of the weakest storms, although the intensification of hurricanes for the Atlantic that is projected might lead to an increase in the number of Category 4-5. So that is the message that seems to be coming out from these experiments, although there seems to be a great deal of uncertainty, as can be seen by those individual dots there. Now, those are the results of work in the past few years. Now, where are we going now? Where we would like to work towards developing a more unified framework by which to address all these timescales. As you saw, there's each one of those results that I showed was focused on a different timescale and used a different tool. We would like to use high-resolution couple modeling systems in order to build, let's use the word seamless prediction system across timescales. And our target model, or model that we're jumping off from, is the GFDL CM 2.5, which was recently described in a paper by Delworth et al. And it seems to be one of the better models of the current generation, at least at reproducing the climate across the world. And we're leveraging off the fast computers, that is Gaia, that we have access to use improved resolution to try and yield improved predictions of large-scale climate, but also get to regional extremes. Now, our current target is to try and say something about regional climate over land. And one of our goals is to outperform our current forecast system, GFDL CM 2.1, which has a 2-degree atmosphere and land resolution. Now, just to illustrate what the added resolution of our new high-resolution model gets us, on the right panel there you see a plot of precipitation as you would see it in the northeast United States on the top with our old model, and on the bottom with our new model. Our newer high-resolution model gives us at least the necessary conditions to get to regional scales. We also want to beat the overall performance of CM 2.1. CM 2.1 so far seems to be a decent model. The skill evaluation of real time of CM 2.1 in the North American multi-model ensemble presented on the left shows that at least for last year it was a pretty decent model. A lot of that had to do with the fact that the model predicted a heat wave, and a heat wave did occur. Whether the model predicted it for the right reasons or not, we were not sure yet. Now, going to high resolution doesn't just get us the ability to go to small scales, but it also improves our representation of the large scale. Just wanted to illustrate in this figure that our representation of ENSO, of El Nino in the tropical Pacific, improves when we go to this high-res model. We get a better separation of the warm anomalies from the maritime continent. The precipitation regressions onto Nino 3 are improved. And so we hope that we might be able to get a better representation of the teleconnections coming from El Nino. Our initial tests of retrospective forecasts from 1982 to 2012 with this new high-res forecast system have been very encouraging. On the left, we show the retrospective correlations of predicting Nino 3.4, that is temperatures in the central equatorial Pacific, a good index for El Nino relevant to teleconnections, with yellow colors indicating the best scale. And what we see is that relative to CM 2.1, the model that we've been using so far, the high-res model improves the retrospective correlation. Not only is there improvements in retrospective correlation for large-scale climate indices, but also for precipitation over land. Shown on the right is a pattern correlation for the difference between 97 and 98 El Nino and La Nina. And the new forecast system, indicated by the red bar, shows very high global correlations. Now, this is very encouraging, and Li Wei Jia, a postdoc funded by MAPP at GFDL, has shown that this is a much more general improvement over land, and these results are being written up right now. Now, getting back to the original theme, which was tropical cyclones, this model in a coupled context reproduces some beautiful tropical cyclones, as can be seen on the top right panel, comparing a coupled model forecast from actual. This is 300 seasons of forecast compared to the left, which are the observed tracks. We get pretty decent density in the North Atlantic, and so we have a system now that, because it's a fully coupled model, that we're able to initialize, where we are able to explore in a relatively seamless fashion a whole variety of timescales, explore the impact of initialization, explore the impact of radiative forcing and how they come together to explicitly target these climate extremes. And we have results that we're in the process of writing up that document what the new sort of things that we've been finding. And I'll leave it at that. Thank you.
Okay, great. Thanks a lot, Gabe. What I'm going to do now is go to the phone lines. If everyone would mind muting their phones before we do questions, unless you have a question, it'd be appreciated. Okay. So are there any questions on the phone line?
In that slide that shows the model tracks, I wonder why the model is populating the south of middle Atlantic with more storms than observed.
So as you correctly note that the South Atlantic has more storms in the forecast than observed. Part of that is a model bias in the South Atlantic, and part of that is that we're showing 30 years on the left and 300 years on the right. But there is definitely a bias. It is not as gross as previous biases. So there's only, I think it's 20 storms in 300 years. So, you know, we have one storm in 30 years. So, you know, we still need to cut it by a factor of 3 perhaps, but we're doing pretty decent relative to other models. This is also a fully coupled model, so.
Are there any other questions?
I have a question. Oh, sorry.
No, please, go ahead.
Okay. I was just going to ask, Gabe, I'm not sure if I heard the resolution of FLOR, and if you use, well, you said it's fully coupled, so just the resolution.
Oh, sorry, I didn't go into that, and I should have. It is a 50-kilometer atmosphere in a cube sphere. And the ocean is a low ocean resolution. So FLOR stands for forecast-oriented low ocean resolution. We've realized that even though we have high ability to run high resolution, we can't do everything. And so we've decided for this application to focus our resources on the atmosphere and land. Because on experiments finding that a lot of the gain that we get from going on CM 2.5, which is a 50-kilometer atmosphere, 25-kilometer ocean, we recover with a low-resolution ocean.
Okay, thanks.
I have a question, please. This is Cecile Penland. I wonder if you could go back to your forecast of Nino 3.4. That one. It seems to me you have less of a spring predictability barrier than many people claim about. I mean, have you looked at that to compare the spring predictability barrier for the El Nino forecast with other models?
So we've only done a detailed comparison to our own model. Part of and there is a improvement. And I'm not sure that this is our best shot. I should have noted that here we're using the initial conditions from the low resolution model in the high resolution model. That's another reason why we've gone with a low resolution ocean. We can just take initial conditions, although the system isn't as balanced as it could be. So I think that we could do even better than this. We get about an extra month in the spring relative to the low res model, and I don't fully understand why. These are new results. They're only a couple months old. So.
But the whole point being that this barrier may not be intrinsic to the system. It just may be how people are doing their predictions.
Or at least the severity of the barrier. It may need not be harsh as it is.
Thank you.
Okay, thanks for all the questions, and Gabe, thanks for the stimulating talk. I think we should move on to the next speaker, which is Schemm. Jay, are you on the line?
Yes.
Okay, I'm going to try transferring control over to you. I think I may have to fiddle around for a moment just because the host computer crashed. Bear with me for a minute. Yeah, everybody please bear with me for a minute. I'm having some technical issues here. Okay, Jay, you still there?
Yep.
All right, I'm transferring control over right now.
Okay.
Well, just 2 minutes. So just go to the share menu and click My Desktop like we did before. Okay, great. Whenever you're ready, go ahead.
All right. Following the Gabe's talk, I'll be focusing more in the seasonal time scale and introduce the dynamical hurricane season prediction system at the NCEP. I'll be briefly discussing about the procedures we follow in issuing the NOAA hurricane season outlooks, and then give some details on the T382 version of the CFS we are using for the hurricane season prediction runs, and talk about some of the tropical storm statistics and performance of this particular version of the model, and conclude with the impact of the dynamical input on the NOAA hurricane season outlook performance. For the 2013 hurricane season outlook, we just issued on May 23rd. The outlook is composed of the type of season and probabilistic sense, whether it's above normal or near normal, below normal activity is expected. And then we give the ranges and the number of the named storms, hurricane season, hurricanes and major hurricanes, and then the total season intensity in terms of accumulated cyclone energy index. In issuing this 2013 hurricane season outlook, we utilized 11 prediction tools. 3 of them, this table illustrates all 11 tools, 3 of them which are the purely statistical method, and 4 hybrid dynamical and statistical method, 3 of them based on the CFS version 2, and 1 from the GFDL hybrid Gabe just introduced. And 4 dynamical model prediction, 1 of which is the T382 CFS, and 3 of them are coming from Europe, ECMWF and EuroCIP and UK Med Office prediction. So there are all the combination of these 11 tools and 7 forecasters' intuition goes into in the making of the hurricane season outlook. And now I'll go into the dynamic component of T382 CFS system. This project has initiated in 2007 as a internal project of the climate testbed activities in collaboration of EMC. And we configured this high-resolution version of CFS in the mix of the atmospheric component coming from NCEP GFS weather forecast system at the time in T382 resolution, which is coupled to NOAA land surface model and GFDL MOM3 ocean model. And we evaluated the performance of this prediction system by making hindcast runs for the hurricane season and for 28 years of from 1981 through 2008. Each of these runs we initialized with NCEP DOE reanalysis 2 and NCEP GODES for the ocean condition. And the first set of the experiments were all initialized in the middle of April, so that we will have the results analyzed for our first May outlook, which is issued in the middle of the May. And then we had a second set of experiment with the July initial conditions. Each forecast extends out to the December 1 to cover the entire hurricane season, and output was saved at 6 hours. And we use the tropical cyclone detection and tracking method based on the Camargo and ZBF. And I won't go into the detail of this method, but the detection thresholds we use for following and detecting the storm uniquely depend on based on the hurricane, the CFS Hindcast results. And for the verification, we use the National Hurricane Center HUDAT and the Joint Typhoon Warning Center best track data sets. And we do not include in the counts the tropical depression and the subtropical storms. Briefly illustrate the performance level of this particular version of the CFS. This is now illustrates the environmental conditions which are relevant to the the tropical storm activities. Top panel shows the interannual variability of Nino 3.4 SST index over the 28 years, and which is compared to the observation. And the middle panel shows the same for the Atlantic Main Development Region SST forecast, and the bottom panel is the Atlantic Main Development Region shear index. And all three indexes, the skill level indicates the fairly good at about 0.7 and 0.75 level. So environmental conditions are fairly well predicted in this system. And the next figure illustrates the climatological characteristics of tropical storm activities in the northern hemisphere ocean basins. Top panel shows the climatological seasonal cycle of the tropical storm in terms of numbers for each month period over the Atlantic basin, middle one for the eastern North Pacific, and the bottom western North Pacific. So this particular version of the model has a very good seasonal cycle over the Atlantic sector. And eastern North Pacific, the season seemed to be starting somewhat slower, but then catch up in the latter half of the season, while the western North Pacific, the beginning part of the season is very well captured and then declines much faster than observed. For the interannual variability of the tropical storm activities, again, Atlantic at the top, eastern North Pacific in the middle, and western North Pacific. It has very good interannual variability captured over the Atlantic sector. It also includes the increased storm activities post-1995 period. For eastern North Pacific, it's having hard time capturing that shifting the trend in the middle of the period. So the skill level is much lower than compared to the Atlantic sector, and western North Pacific sector has a fairly good skill level in predicting the interannual variability. And now we're going to the real-time prediction verification. So this system has been used for real-time prediction for the last 4 years, from 2009 to 2012. And this table shows the verification statistics in terms of the number of storms, hurricanes, and ACE index. And the verification is given in the third row of each year group. And last 4 years, the system has been able to predict storm activities very well, but below normal activities for 2009, much above normal activities in 2010. And again, above normal activities in 2011 and 2012. The next, even though the hindcat verification didn't show much of a skill level for Eastern North Pacific, the real-time prediction has been shown very skillful over the Eastern North Pacific for the 2009 through 2012. And now we're looking at the track predictions coming out of these dynamical predictions. Again, for the 2009 through 2012 year, top panel shows the actual observed storm tracks for those 4 years, and bottom panel shows the predicted tracks in terms of anomalous track density distribution, because the nature only provides you the one realization per season. These prediction runs have multiple realizations. Each of them comprise of more than 15 member ensembles. So again, we are looking at the track density distribution. The T382 CFS captures that shifts in the track positions for each individual seasons pretty well. For instance, in 2010, it predicted a very hyperactive season, but most of the tracks seem to be staying out in the open ocean. Very few, small percentage of the tracks is actually making landfall, making the tracks approaching the land area. And 2011, again, it's predicting the above normal season activity, but this time the tracks seem to be somewhat closer to the U.S. mainland, which is quite comparable to what was observed. And the same goes for the 2012, and it even has tracks emulating something like the Hurricane Isaac and even Sandy-like tracks along the East Coast. So we have, and then the next we will take a look at how well this dynamical prediction input has contributed towards the NOAA hurricane season outlook. Now, this slide illustrates the skill level of the hurricane season outlook for the Atlantic Center for the entire 14 seasons. We have issued the outlooks since 1998. For the MAPP outlook, we correctly predicted 70% of the season, and in August update, that correct prediction percentage went up to about 80%. When we divide this 14-year period into two periods, where most of the outlook were issued entirely based on the statistical method in 1998 and through 2007, and that's compared to the skill levels of 2008 through 2012, when CFS, the products based on CFS has been introduced. So pre-CFS period, May outlook was 40% correct, and August update was 62%. Compared to that, once post-CFS era, the May outlook had predicted 80% correctly, and August update has increased to the practically perfect. So the dynamical prediction input has contributed significantly in improving the skill level of the hurricane season outlook. So in summary, T382 CFS prediction system has shown a very robust climatological seasonal cycle and has a fair level of skill in predicting interseasonal storm activities over the Atlantic and West North Pacific basins. Addition of the dynamical system has contributed considerably in improving the hurricane season outlook performance since 2008. We are sort of looking into ways of utilizing the track position information for possible probabilistic landfall distribution predictions, and we are currently trying to improve upgrade this system to a somewhat higher resolution to T574 or higher by 2015, and also incorporating the NOAA NMME forecast products for the enhancing the tools we utilize for the hurricane season outlooks. I'll stop here and take any questions you might have. Thank you.
Thanks a lot, Jay. That was very interesting. I'm going to go to the phone line. If everybody could please check and make sure you're muted unless you're going to ask a question, that'd be great. Are there any questions for Jay?
I have a question. This is Yolanda. I wondered if you have an outlook product for the Northeast Pacific, or if that's something of interest that you would be developing.
We do issue the Eastern North Pacific outlooks, yes, and Central Pacific also.
And do you have similar results with the inclusion of the CFS?
Eastern North Pacific, we haven't really looked into in detail as in the Atlantic sector, but from looking at the performance of Eastern North Pacific real-time prediction, I am confident that we have a comparable performance improvement in the hurricane season outlook over that sector.
Okay, thank you.
Are there any other questions for Jay? Jay, I have a question. In your conclusions, you alluded to the probabilistic landfall distribution work, and I know that you guys are getting started with that now, but do you have any preliminary sense of skill there? I noticed in one of your graphs you alluded to a Sandy-like or an Ike-like track, and so I'm wondering if you can comment on that or if it's just too early.
It is too early. We've been looking at the real-time predictions last 4 years, and we sense that there is some merit to analyze these track predictions more carefully so that we can apply the landfall possibility. But since it's such a sort of infrequent event, it's really hard to come up with something concrete way we can say this is definitely going to help in predicting the landfall possibility as yet.
Yeah, it's interesting. Ken Mooney just pointed out that on the slide you have up right now in 2012, there is one track there that looks just like Sandy. All right. Jay, thanks so much for the talk. Very interesting. Our next speaker is George Hallowell. George, are you on the line?
Yes, I am.
Okay, great. I'm going to switch control over to your computer.
Okay. Can you see it now?
Yeah, it looks good. Just go full screen, and whenever you're ready, go ahead.
Okay, thank you. Well, today I'm going to be talking about the work we're doing here in Miami using observing system experiments and observing system simulation experiments for the general purpose of improving our ability to monitor the Atlantic warm pool, and then as a result, potentially improving hurricane forecasting. And in this talk, I'm going to demonstrate that the accurate monitoring of the Atlantic warm pool is important for hurricane forecasting both seasonally and for individual storms. And I'll be focusing on how we're using OSSEs and OSSEs to do this. This work is in its early stages, so for the bulk of this talk, I'm going to be describing our new ocean OSSE-OSSE system and summarize how we validated it in the Gulf of Mexico region. And then at the end, I will just discuss how we're going to be using this system to evaluate observing systems for the purpose of Atlantic warm pool monitoring and how this may improve hurricane forecasts for individual storms and potentially for seasonal forecasts. Okay, one key important fact about the impact of the warm pool on hurricanes is that it's primarily the thickness of the ocean warm surface layer where the water is greater than 26 degrees Celsius. It's more important than the actual value of sea surface temperature because most of the SST cooling beneath storms results from entraining cold water from the deeper ocean. And where the warm layer is thin, you can have cooling of several degrees Celsius. Where it's thick, cooling is inhibited beneath storms, and of course you can tend to maintain stronger storms in that situation. So for hurricane forecast models, the warm pool structure must be accurately initialized in any forecast model, and that's important for individual storm forecasts, and it's potentially important for trying to forecast seasonal evolution of the warm pool prior to hurricane season. Accurate initialization is important, and that is where ocean observations come in, which constrain the upper ocean structure in the near real-time ocean analysis products that are being used and will be used to initialize ocean forecast models. And such products may include the European Mercator or the Navy's Global HICOM analysis product. And OSSEs and OSSEs are going to be used to determine if the existing ocean observing system is adequate or needs to be enhanced to improve warm pool monitoring. So that's sort of where we're going. And to illustrate the situation, I show two maps here. On top, I show the tropical cyclone heat potential, the amount of thermal energy needed to raise the water warmer than 26 degrees Celsius to that temperature. And on the bottom, I show the depth of the 26 degrees Celsius isotherm. So this illustrates the regions in the warm pool region where the warm layer is thick and where you have the greatest potential for the ocean to maintain strong storms. And it's not only just the general structure of the warm pool region, but it's the mesoscale structure in that region that's potentially important. You can see by the details of the structure. These maps were generated from the Navy's Global HICOM analysis system. So and I just calculated these maps from the model analysis output. Just for those who are not familiar with OSSEs and OSSEs, OSSEs are used to assess existing ocean observing system, where you run twin experiments, one where you assimilate all observations, one where you deny the observing system of interest. And then based on the error increases in analysis, in ocean analyses or forecast initialized by that analysis, you give a measure of the impact of the observing system that was denied. OSSEs take that a step further, where instead of using real observations, you simulate synthetic observations for a nature run that's deemed to represent the true ocean. And here you not only can assess existing observing systems, but you can assess the impact of new observing systems or alternate deployments of existing systems, where you can use OSSE systems to design field experiments. And I'm going to show how these systems are evaluated before you can perform valid OSSEs. And that's done by performing observing system experiments and then performing the exact same experiments using synthetic observations. And if you do this side by side and you determine that your OSSE system with synthetic observations produces the same impact assessments of existing observing systems, you can deem the system to be validated for the future experiments where you evaluate new or altered observing systems. And the OSSE system that I'm describing has been developed here at Miami at what we call the JOML CMS Ocean Modeling and OSSE Center. And the initial system we configured is based on the hybrid coordinate ocean model using two different configurations for the nature run and the ocean forecast model. we've worked on a new research ocean data assimilation system. And an important point about our system is that we've employed strict design criteria and used rigorous evaluation techniques that have been developed for atmospheric OSSE systems but have not yet been completely implemented for the ocean. So we're sort of building upon ocean OSSEs have been performed before, but we're trying to build in the techniques, all the techniques that have been developed and long used in the atmosphere to try to make sure that our impact assessments for new systems are actually valid. The system was initially configured and validated in the regional Gulf of Mexico domain, and we will very soon expand it to the full Atlantic warm pool domain. Now, I'm going to show the result of the system validation in the Gulf of Mexico. Just one example of how we declared the system valid, where we used aircraft airborne profile surveys that were deployed in the Gulf of Mexico during 2010 during the Deepwater Horizon oil spill on 9 flight days. And I show a atypical flight pattern there for 9 July. And these provided valuable observations to evaluate the OSSE systems I'll illustrate here. To do that, I've performed experiments using OSSE experiments as shown here, where one experiment assimilated all observations, as shown in the list there. A second experiment where I denied 2 of the 3 altimeters that were assimilated, and the third where I denied all observations, or in other words, an unconstrained simulation. Now, using synthetic observations derived from a nature run, I repeated those 3 experiments, but simulated synthetic instead of real observation. The question is, do we obtain the same impact assessments from the OSSE and OSSE experiments? And the answer is yes. The 4 panels shown here, the 2 on the left show results from the OSSE experiments where the model fields were compared to actual observations. The top left panel shows compare RMS errors for temperature over the upper 250 meters, evaluated on the 9 flight days of the aircraft observations that I showed before. And on the bottom, the depth of the 20-degree isotherm depth, which sort of serves as a proxy for the structure of ocean features in the Gulf of Mexico, old current system, and associated eddies. And the blue curve is the result where all observations were assimilated, the red curve denying 2 of 3 altimeters, and the black curve where all observations were denied. The important point here is that the panels on the left show the same results for the OSSE experiments, where the RMS errors are compared against the nature run, and we see very, very similar results. So this along with other evaluation steps that we've taken, have given us confidence that the OSSE system will give us reasonably realistic impact assessments. And as one example of an OSSE that has just been performed, I'm looking at the impact of horizontal profile resolution in rapid response airborne surveys that can potentially improve ocean forecast model initialization. I ran experiments where the observations listed here were simulated over 4-day analysis cycles run at 7-day intervals. And in addition to the satellite and in situ observations, I assimilated airborne profiles. And these profiles, synthetic profiles, consist of 1,000-meter AXTTDs, temperature and salinity profiles. These are compared. I compared 3 experiments where the airborne profiles were on a 0.5-degree horizontal grid, a second where they're at coarser resolution, a 1-degree grid, and a third experiment where all observations except the airborne profiles were assimilated. And this is the domain I looked at. The larger dots show the 1-degree grid, the NL dots show the 0.5-degree grid. And the results from this OSSE test, the blue curve shows the RMS error, and on the top panel, that's for the tropical cyclone heat potential in kilojoules per square centimeter. The black curve shows the result where the airborne profiles were denied, but all other observations were assimilated. And you can see that the airborne profiles substantially reduced the RMS errors in the ocean analysis products over a several-month time interval during 2010, which means that you'll be providing substantially improved initial fields to any forecast models initialized in these fields. The red curve shows the result for a 1-degree profile grid, and this illustrates the importance of mapping the ocean fields with relatively high resolution to substantially improve the initial fields for hurricane forecasting. The bottom panel shows the same result for sea surface height, and these are, of course, compared to the result for the nature run. And again, you can see improvement in the structure of the ocean features in the Gulf of Mexico region. And this is the type of analysis where you can begin to get a feel for how certain observing systems, the value of these observing systems. And in this case, the airborne profiles can be quite valuable in regionally improving ocean fields for forecasting. Also, in addition to RMS errors, we reduced the mean bias in these fields. And I show this for the tropical cyclone heat potential. Again, the same 3 experiments where the bias is actually reduced to near 0 with the higher resolution profile grid. And like I alluded to earlier, this work is in its early stages, and we're now porting this OSSE system to a larger Atlantic domain where we'll be looking at issues related to monitoring the Atlantic warm pool. And there are some questions we'll be addressing. I have a list of questions we'll be looking to address in the very near future using OSSEs to assess the impact of existing observing systems, surface drifters and Argo profiles, and repeat XPT transects. And they will be using OSSEs to look at new and enhanced observing systems that may improve monitoring the Atlantic warm pool. For example, is there value to adding thermistor chains to surface drifters and surface meteorological buoys? Would additional XPT transects be helpful, particularly in the Caribbean Sea and Gulf of Mexico, where Argo floats are rarely present? And what is the impact of other special observing systems, powered gliders or profiling gliders, again, particularly in the Caribbean and Gulf, where Argo floats are rarely present to constrain ocean models in the warm pool region? So I will conclude there and take any questions.
Okay, great. Thanks a lot, George. I'm going to go to the phone lines, or I don't know if there are any questions here in the room. Any questions on the phone? Okay. Well, George, thanks a lot for the presentation. Very interesting work. So our next speaker is Chunzai Wang. Chunzai, are you on the line?
Yes, I'm here.
Okay, great. I'm going to try transferring over to your computer. And just share your desktop. Great. All right, looks good. So whenever you're ready, go ahead, Chunzai.
Okay, I'm ready. Hello, everyone. This is from AOML. Today, I will talk about the relationship of the dust with the AMO and the hurricane. The major focus is on the multi-decadal time scale. And the talk is based on our recent paper, which is published in Journal Climate. We first take a look at the early study. For the climate part, there's one paper published in 2008 in GRL, and basically this paper used a short data set from 1980 to show trend in Atlantic acidity and rainfall in Sahel and dust in Atlantic Ocean. So basically here shows the acidity continuing increase, and rainfall anomaly over Sahel is also increased. However, the dust over tropical North Atlantic is continuing decrease. This is the climate. And also the hurricane part of the study, there also another paper by Ivan et al. Published in 2006. And this paper used observation from 1982 to 2005. And basically paper show it's a strong negative correlation on interannual time scale between the hurricane and the dust. So basically, this figure shows two curves. One is dust, another is TCD, shows the good correlation. So this is so our study basically used longer dust data, which is starting from 1955, and we also use many ocean, atmosphere, and hurricane data here. I don't want to read here. All this data are available online. So next we take a look at the result. So this slide shows time series of the AMO, Atlantic multi-decadal oscillation, and dust in tropical North Atlantic, and rainfall over Sahel region. The top panel shows AMO, and the shading is 7-year running mean, which we remove interannual variability, and we only keep decadal, multi-decadal time scale. So AMO time series, and this is the rainfall over Sahel area, and the bottom panel shows the dust over TNA region. So basically, when AMO is in negative phase, so the Sahara rainfall normally is negative. However, the dust over TNA region is positive. And similar situation, if AMO in positive phase and rainfall anomaly over Sahara region is also positive, and the dust over TNA region is negative value. So this is, and we also use longer data set. This two-time series shows AMO and the Sahara rainfall in entire 20th century. So basically, the relationship still hold. When AMO in positive phase, the Sahara rainfall anomaly is positive. When AMO is in negative during early time, and rainfall also, anomaly also is negative. And this slide shows spatial rainfall pattern related to the AMO and the dust over TNA region. So the top panel shows the regression of rainfall anomaly onto the AMO index I showed you earlier. So the obvious structure over Sahara area is a strong positive regression. What does it mean? When AMO is positive phase, rainfall anomaly over Sahara area increase. And if AMO in negative phase, rainfall over Sahara area is negative. And the low panel show regression of rainfall anomaly onto dust time series. Again, a strong negative correlation over Sahara area is strong negative, which means rainfall anomaly is positive, then dust over TNA region is positive. So this is so next we take a look at the vertical velocity, atmosphere vertical velocity at 500 millibar. So basically, the slide shows the regression of the vertical velocity onto AMO index. So again, you see the strong negative value here, which means when AMO is in positive phase, the atmosphere 500 millibar have a strong upward motion, which is consistent with rainfall slide I just showed you. This positive vertical velocity is associated with the positive rainfall anomaly. And this vertical velocity is from NCEP analysis field. And the rainfall data is from GPCC data set. The two data sets are independent, but the result is consistent, which means the result is robust. So this is the next. So this slide shows the relationship of the wind with the dust. What we show here, we calculate here is the regression of 700 millibar wind onto dust time series. So it's obvious feature is a strong easterly wind over equatorial Atlantic Ocean, strong easterly wind here. And this strong maximum easterly wind anomaly is inconsistent with the maximum dust band, which is between 20 degree and 20 degree north. And this position inconsistent see suggesting the dust change in TNA region is not due to the wind anomaly. So here we hypothesize the dust is due to the increase of dust production over Sahel. And second, this increased dust over Sahel is transported by mean zonal wind instead of wind anomaly. So we first prove the first hypothesis, which means the dust production is increased in Sahara area. Then here is the result. What we show here is the wind composite. The shading here in this plot is the wind speed, and the vector is wind, surface wind. And the top panel shows NCEP NCEP field, and this middle panel shows ERA 40, and last panel shows the 20th century real analysis field. And a consistent result between these three plots is over Sahara area. There's a strong positive wind speed over there. And because the dust production is proportional to the wind speed cube, so this plot suggests the dust production over Sahara area is increased during the cold field AMO. So basically, we prove the first hypothesis. Then we take a look at the second hypothesis, which means the dust transport due to mean state instead of wind anomaly. And then here we plot here is the top panel shows the zonal wind at 0 degree longitude. This is the height and this is latitude. So basically over here we have a strong easterly wind. This is so-called Africa easterly jet. And the second panel shows the wind at 700 millibar. The shading is the wind, zonal wind only. So what we see here is a strong maximum easterly wind over between the 20 degree north, which is consistent with the maximum dust band also between the 10 and 20 degree north. So this suggestion, this strong wind suggesting the dust if is increased over Sahara area, then this mean zonal wind can carry out the dust from Sahara area into the TNA region. So far we show our result suggesting a positive feedback between the AMO and the dust through the Sahara rainfall anomaly. So here is how this positive feedback works. Suppose we have a positive SIT anomaly over TNA region. Then this positive SIT anomaly will shift ITCZ northward. And then we have a southwest monsoon wind anomaly. And this monsoon wind anomaly will increase Sahara rainfall and then decrease dust in Sahara area. We prove that. And this decreased dust production in Sahara area will produce with a smaller westward dust transport. And then we have a low concentration of dust in TNA region. And this low concentration of dust in TNA will further increase the positive SIT anomaly over TNA region. So the whole loop is positive feedback. Next, we move to the hurricane part. So here we show the relationship between dust and hurricane on multi-decadal time scale. Again, we perform a 7-year learning mean, which we remove interannual part, only keep decadal, multi-decadal variation. And the black curve is dust, and the red curve is the hurricane, number of Atlantic hurricane. So when dust anomaly is positive, and the hurricane number is small, and if the dust over TNA region is a negative value, then Atlantic hurricane will have more Atlantic hurricane. The mechanism is due to the dust induces the vertical wind shear. Then we plot the vertical wind shear and the dust. Now, again, the black curve is the dust, and the red curve is vertical wind shear in the hurricane developed region. So basically, when dust is a positive vertical wind shear is stronger, which is unfavorable for hurricane. And we also calculate the regression, and this figure shows regression of the vertical wind shear on dust. What we saw here is a strong positive regression over hurricane may develop region. And this strong vertical wind shear is unfavorable for hurricane. This is why we observe an inverse relationship between the dust and the Atlantic hurricane. So here is the summary of my talk. First one, we show multi-decadal co-variability of the MO and dust in TAA and rainfall over Sahel area. And the second one, our result suggests a new mechanism for North Atlantic ST variation on multi-decadal time scale. And this is so-called positive feedback between AMO and dust through the Sahara rainfall variation. And another conclusion we found here is dust vary inversely with the number of Atlantic hurricanes. And the mechanism is due to dust induce the vertical wind shear in hurricane may develop region. The last conclusion, not conclusion, the implication of this study is, we have so many couple models right now that in order for models to simulate Atlantic climate, your couple model must be able to simulate the aerosol related feedback. This is our suggestion, our implication. So basically, I stop here. If you have any question, we can discuss together. Thank you.
Yeah, thanks a lot, Shunzai, and that last summary point, that motivational summary point for model development. I'm going to go to the phone line. Are there any questions on the phones for Shunzai?
This is Ram from GFDL. I have a question.
Yeah.
Interesting talk. I was wondering whether you could comment on anthropogenic aerosol-induced feedbacks. By dust, I presume you've been referring to mostly the natural dust.
Yeah, exactly. Actually,
so would you care to comment on what anthropogenic aerosols may have been doing over the North Atlantic?
Yes, actually, I think most people know this paper, right? This paper published in last year and this paper basically they argue the anthropogenic aerosol is very important for the AMO, and however the model cannot produce the multi-decadal variation. Here the model result. This is the observation, okay, dust, and this is the model result. Basically, model result have no multi-decadal variation for the dust, and this is one paper for this. And from our paper, we saw this relationship is this. So this time series basically shows this. This is North Atlantic ST anomaly including linear trend, and this is the remove linear trend, and this bottom two panel show is rainfall, similar, including linear trend and the remove linear trend. So basically, the global warming effect and AMO on the Sahara rainfall is opposite. So basically, global warming will reduce the rainfall over Sahara area. However, the AMO positive fee will increase the rainfall over there. So there's also other model to show this result. I hope I answer your question.
Are there any other questions for Shunzai? Okay, thanks a lot, Shunzai. I appreciate it. Next speaker is Yolande Serra. Yolande, are you on the line?
Yeah, can you hear me?
Yeah, I'm going to transfer control over to your computer right now.
Okay, can you see my my presentation?
Yeah, looks good. Whenever you're ready, go ahead.
Okay, so I'm going to talk about some dynamical downscaling we've done with the HAD-GEM 2 ES, which was well performing in our region. So I'll go over some of how we got to that point. First, I wanted to just say that we focus on tropical easterly wave tracks, and because of the nature of this talk today being on extreme rainfall in the tropics, I thought I'd just show that this news broadcast here, news story on the left is from a newspaper in Venezuela, where they talk about the first tropical wave of the season. So they're concerned very much so with the with these waves and how they come in, and it affects flooding and that sort of thing in their region, and also in Central America and in Mexico. This is a equivalent to SMN, the equivalent to NOAA, National Weather Service forecast for Mexico, and you can see the wave troughs being shown. And so heavy rainfall is associated with these waves, and so they are associated with extreme events south of us. And then also, of course, with hurricanes. And here's a satellite image of a Hurricane Jova, which came in October 2011. It was associated with an easterly wave, and you can see this inverted V in the satellite imagery. This is the remnants of the hurricane, and it made the newspapers. It impacted a resort on the west coast of Mexico. It's also interesting to look at these tracks because of their impact, because of what's happening in the region according to the climate projections. Here's some results from Maloney et al. 2013, which was a task force joint paper. I believe these results were presented by Nealon, where he shows the temperature anomalies in the region, all of North America. But if we just focus on our region as being the Inter-America Sea and East Pacific, we see that less so in December, January, February, but in June, July, August, we have strong temperature anomalies with the RCP 8.5 scenario by the end of the 21st century, 2070 to 2099. And importantly, in the precipitation differences, we also see that this region, even more so than the western U.S., is, and in both seasons, the winter and summer, is experiencing strong drought. So it's an important area for looking at rainfall extremes. Okay, so our work, we looked at both. So these are the storm track densities of easterly waves. It does not exclude hurricanes, but these are coarse models, and so it's probably just, picking up perhaps strong storms in these models, but the coarseness doesn't allow them to really spin up hurricanes. So these are primarily easterly wave tracks, and this is for the RCP 8.5 scenario. About 9 models were taken for this multi-model mean. This is the standard deviation, and here we see the difference from the historical period, and we have a southward shift in the tracks, and this is consistent with CMIP-3, which sparked this investigation in the first place, where the results showed a southward shift. And we were interested in what impact that would have for the rainfall of the region. So we were just confirming that it also existed in CMIP-5. Here are the track strengths. So these are based on 700 millibar vorticity tracks. I should have said that. So this would be then the strength of the low centers, these closed vorticity center strengths. And so here we see that strengths typically are on the northern edge of the ITCZ, where the storms are expected to spin up. So you get stronger storms. Any kind of estimated storm from these coarse models would be in this region, and this is the standard deviation again, and the difference from the historical period. We see here that the most significant changes, there's not quite as big of a pattern or significant of a pattern in the strength as there is in the density of the tracks, but there seems to be fewer tracks here in the West Atlantic, southern West Atlantic, perhaps a hint of more tracks here, but again, the more significant results appear to be in the track density rather than the track strength. Okay, so one thing we looked at, and it's associated again with more the lack of rainfall rather than strength of rainfall, is that this is the, again, this the results for mean track density for the 4.5 and the 8.5. This is our work looking at the course models, and we see this shift. It's stronger in the warmer projection with the warmer scenario, the RCP 8.5. Chris Karnauskas has looked at the precipitation for the same time period. He looks at 8.5 change of precipitation for June, July, August, and September here. And what he shows is that there is an increase in precipitation to the south and then a deficit here along the Mexican coast. We see that more pronounced in the middle of the summer and then still there but less pronounced winds in the September and June period. And so he did another analysis where he looks at the intensity of this drying, and he calls this the midsummer drought. And he shows this is the historical period here. Then we see 4.5 and 8.5, and we see that this drying is becoming more intense with the warmer, the more intense warming projections. And so we want to look at the relationship between this deficit in rainfall and this shift in the storm tracks in this region. So that's one thing that this project is going to look at. The other thing we've done is to assess the models in various kind of important regions throughout the IAS and East PAC, and one of these regions, of course, is the NAM region, North American Monsoon. So my graduate student has looked at the phase of the annual cycle in the models versus the PNOAA observations, which are shown here in black. And you get a scattering of all the models. We have small phase lag here where the phasing is within a month or less than a month phase lag from the observations. And we can see the models, the bulk of the models tend to capture an onset, but they tend to overestimate the maximum monthly precipitation in the monsoon region, and then they don't end it so well. And this just continues. The moderate phase lag models are those with a 1 month phase lag, phase error, and it just, this problem in the end of the season seems to, be worsened for these models, and then just, you don't even get really a peak for the large phase lag models. These are greater than 1 month off from the observations. You get even worse, not even a peak so much in the summer, it just kind of trends upward for the most part. And then here is the mean. We see the purple here shows the spread of all the models. The dashed line is the all model mean, and the black is the observations. So we note that the two models actually that we're going to downscale. The one I'm going to talk about today is the HADGEM2, and MPI is the one we're working on this summer to downscale. The HADGEM2 and MPI are both small phase lag models. So this analysis was helpful in choosing the models to downscale. So we go to a more rigorous test here where we're looking at the daily data from these models. And this is, again, the annual cycle. And you can sort of see where this problem in the end of the season really is standing out for these models versus the beginning of the season. There really are there's just too many rain events in the latter half of the season for these models. And the top here is the trim daily data at quarter-degree resolution, and here's the multi-model mean. These lines here are thresholds for determining the onset and retreat. One is with respect to the trim data, and it's the same for all models. The other one is a model relative threshold. And from those results, Carrie finds that here we see that the median onset for the trim is 19 June, and the median retreat is 28 September, and what she found was that the models were typically early for the mean onset during the historical period, and it's uncertain because of the amount of spread what the mean retreat date. It's just there's not a consistent story here with the model, either with the absolute or model relative threshold, and the standard deviation is much larger than what's seen in the observations, and that's consistent with what I just showed you. So this type of analysis also was helping us to choose models to downscale to examine the shift in the easterly wave tracks. So our main objective of our NOAA MAPP project was to downscale the models that performed well, and So we've done, excuse me, we've done that for the 1977 to 2003 and 2069 to 2097 period for the RCP 4.5, which was the data available at the time we started the downscale. Now 8.5 is available, and we're considering doing that as well. We have it at 35-kilometer resolution over this domain. It actually goes out a little bit further, but this is the primary focus of our downscaling efforts. We're starting the MPI downscaling as we speak, actually, and we're going to do the 4.5 and 8.5, also at 35 kilometers. And we're going to look at, again, the impact of this track shift on the rainfall in the region. And we're going to revisit forcing mechanisms as well for these waves, given the shift, what might be causing this shift. Okay, so here's some results for the downscaled Hadley runs. First, I'm going to compare to the historical observations in the course model. So the top here are the TRIM 3B42. These are the daily data at quarter-degree resolution. And you see that the PAD GEM2ES has the general features of the TRIM. It has the monsoon signature here and the ITCZ. This is for just the summer, June through September. And I matched the time periods here, 1998, 2003 from HAD to the available TRIM data, 2003. I ended in 2003 because that's when our downscaling ends. Okay, so we see that there's the general features are there, but it lacks the lighter rainfall contours here, and it doesn't have the more intense rainfall contours in the ITCZ, probably mainly to do with the scale of the model at greater than 1 degree. So here's our downscaled results, and you see that this looks far more like the TRIM data. We have the topography in the downscaled run to capture the forcing over the mountains, which is important in the the NAM region, and of course all along in Central America. And you see that signature. You also see it here in South America, and then the ITCZ is more intense than in the original forcing data. We also see more light rains occurring here in this region, like in the TRIM. The one thing we did notice is that where it's drier in the TRIM, as in this region compared to the ITCZ, for instance, the model is actually even drier. And where it's wet in the TRIM, it's even wetter in our model. And this is a common problem. This is not a convectively resolving scale. We run it at 35 kilometers, so we rely on the convective parameterization schemes, which do tend to they're a little overzealous, so they overestimate rainfall. But overall, we're happy with the results in the region. Okay, so if we look at, one thing I looked at was I just differenced our RCP 4.5 to the historical in terms of rainfall, and I get that southward shift that Chris showed in his results in the Maloney et al. Paper. And here again, I'm just reproducing our track density differences to show the consistency with the tracks, the synoptic wave tracks. And overall, then, this is just showing the historical summer period to our downscaled summer period for the future, 2069 to 2097. And you see some of the results. This is the boundary of our model. That's why it's not looking quite right. It's a Lambert projection, so the boundary is kind of at an angle here. But you see that the ITCZ appears to be more, it extends more to the west. And we have other differences that are hard to show. I'm going to show a better plot to see the differences next. Well, you can see them here, that there's generally less rainfall in the region consistent with the course model, multi-model results that were shown earlier. Okay, so some of the things I wanted to do were to look at the downscaled annual cycle over some sensitive regions. I chose an Arizona box to see the northern end of the monsoon. I looked at the NAM region that Carrie looked at, and then I look at an East Pacific midsummer drought box, which is essentially a box right over that red bullseye in Chris's plot. And what I have on here, the blacks are all the observations. So the two black lines are the PNOAA and the TRIM. The PNOAA is matching the Hadley downscaled and course model data from 1977 to 03. The TRIM begins in 98. And so, but you can see the TRIM and the PNOAA are in fairly good agreement over these regions. And there's no PNOAA over ocean, so that's why this one only has the TRIM. And what we see is that, interestingly, it has been shown with other downscaled results, is when the course model, which is shown here as the dashed dot line with the squares, has an incorrect, has a problem with the large-scale forcing, you can see the downscaled results don't fix the problem. So where the large-scale forcing is incorrect, and I suspect that's why this region isn't being captured, isn't the extent of the monsoon up into Arizona isn't being captured, perhaps because not of local forcing, but the large scale, that our downscaled results mimic more the Hadley model than the data itself. But this needs to be looked into more carefully. I'd like to look at more boxes over, for instance, New Mexico, and find out the extent, because this box is fairly limited to southern Arizona. So I'd like to see the extent of this problem, and I don't have those results yet. In the NAM region, we see a nice result consistent with the reason why we chose. One of the reasons we chose the Hadley model is that it was able to capture, but it overestimated. We can see that the downscaled results have somewhat corrected that problem, but not perfectly. And they still overestimate in the late season, but in the winter. But we're pretty happy with the overall results for the downscaling in this region. And also for the midsummer drought region, you see that although it's not perfect in June, we seem to overestimate the rainfall in this region. In general, we're tracking the annual cycle with the observations fairly well. Okay, so for the future, looking at the same idea, an annual cycle in the rainfall for the region. In the future, the model does not predict much of a change. So now I'm just looking at the downscaled Hadley. I'm not showing the course model. And black is the historical period, and the gray is the future. So what I'm showing here is just to compare, just to see the difference into the future. And we don't see much of a difference in the Arizona region. In the monsoon region, we see somewhat of an increase in the late monsoon region that's been reported by other studies. Although the difference here, I'm not so confident in based on the historical bias in this region. So this needs to be, taken with a grain of salt, given the historical bias is of similar magnitude as this perhaps increase in the late season. And then we do see a decrease here, consistent with an overall drying that is predicted. So in other words, sort of a shift in the monsoon to later, perhaps by a month. And this needs to be, again, looked at more carefully with the daily data. And we intend to do the same analysis that we've done on the daily rainfall data for the historical period on the future period to get a better idea of this shift and a more accurate estimate of it. This was interesting here in the East Pacific midsummer drought region. We find the results are consistent with the mean rainfall or with the Karnatska's results, that there's a significant drying in the midsummer in that region into the future that's not seen here. And you can see the hint of the midsummer drought in the historical period, and then it's just deepening. It's perhaps not so different in June and September, but it just deepens in July and August. So again, we're going to look at the mechanisms for that and potential relationship to the shift in the synoptic wave tracks. And this wetting here in October is also interesting, and we haven't looked at that yet. Okay, so we also try to examine some of the extremes that we're extreme statistics that we're getting. So here I'm looking at comparing the 99th percentile rain rates for the historical period. These are calculated on an annual basis. So I calculate the 99th percentile event at each grid point for the June through September period in the TRIM data set. And then I compare it and then I take the mean over the, in this case, only 6 years, but in this case, it's a longer time period, roughly 30 years. And there's quite a difference, and I believe that some of this might be the result of the fact that the TRIM data is only available for 6 years. So we can see that this quantity is very sensitive. I've talked to some people that have done more extreme precipitation analyses, for instance, Francina Dominguez here in our department, and she said that these quantities can be very sensitive. And so I need to find a way to do this. Unfortunately, we should have daily data, and so I can go to reanalyses perhaps, but it's going to be coarser. So there needs to be a way to get at a better statistic in the observations to compare. But unfortunately, over oceans, that's a very hard thing to do. So we might just maybe limit it to PNOAA, or well, PNOAA is monthly. Anyway, we're having trouble trying to validate this, but you can see the model over ocean is showing a much more concentrated region of high rain rates than the TRIM perhaps suggests. Nevertheless, we go to the
change.
Yes.
Wrap up in the next minute or so. It would be good. Thank you.
Okay. Thank you. Okay. This is my last slide, actually, and it shows that the 99th percentile rain differences from the future to the historical normalized by the historical values, and you see that there's a big decrease in the Inter-America Sea region, consistent with that overall drying that we saw in the course model for the warming. And these edge effects, this is more because this large bullseye here is because you're having that shift in the rainfall. And so where there were very low rain rates before, it's now a bullseye because the rain has shifted southward. And since we normalized by R99, it's difficult. This happens in some areas where you had very low rain rates. You can see that this is all blue here, so this can be sort of ignored. Just focus on the areas where there's comparable values, but they're somewhat diminished from the historical period. And here I've just reproduced the historical period for the Hadley. So that's it. That's our results so far on this analysis, and we're going to start looking more in detail at the daily data and higher resolution, the diurnal cycle, and so forth, and try to understand the impact primarily associated with this shift in the storm track, but also just the rainfall extremes in the region for the warming model runs. Thank you.
Okay, thanks a lot, Yolande. I do want to allow time for just one really quick question, if there is a question out there for Yolande. Do we have a question on the phone line or here in the room? Okay, so Yolande, thanks for the presentation, and thanks to all of the presenters for the really stimulating webinar today. This is the last webinar in this year's series, so this is the second year we've done this, and you know, I'd like to thank all the speakers from today.
Huh?